Hello, it's David Leroy here, and this series of slides is on the topic of hypothesis testing. And here are some topics that we will explore in relation to hypothesis testing. We're going to be looking at inferential statistics, sampling distribution, the central limit theorem, the difference between null and alternative hypotheses, the significance level, rejection regions, critical values, and some issues to do with directional and non-directional predictions that we make in science. Inferential statistics are used when we make inferences about a population based on samples that we take. If you think about an example or a research question along the lines of, how tall are people in the United Kingdom? Theoretically, there will be population parameters associated with that, right? Out of all of the adults that live in the United Kingdom, there must be a mean height and a standard deviation associated with that. But these are just theoretical parameters because in reality, we're never going to know exactly what the mean for an entire population is. The important thing here to realize is that researchers, because we don't have access to entire populations, draw most of their conclusions from samples that are taken. And samples that are taken from larger populations are smaller, and therefore we are able to calculate the mean and standard deviation quite precisely. So, some logic about sampling distributions, and this is where we need to be aware of the central limit theorem. When we take a sample from a population, the means that we draw from that sample will be normally distributed. So imagine that this figure below is depicting the population sample. This is a theoretical distribution, and if you think of the example of the height of adults in the United Kingdom, we would suppose that it would be normally distributed, that it would have some type of mean and a standard deviation associated with it. But like I said, because we can't access the entire sample, we can't measure the heights of everybody that lives in the United Kingdom, we're going to take samples. So if we took a sample of 1,000 individuals, measured their height, we would end up being able to calculate the mean and standard deviation. Now, what's interesting about taking a sample from a larger population is that average that we are able to calculate is only an estimate of what the true average in the population might be. And so if we were to take a sample of 1,000 individuals, measure their height, we might end up with a average height of 5 foot and 10 inches. If we were to take another sample of 1,000 people, we might end up with an average height of 5 foot and 9.5 inches. And if we were to take another sample again of another 1,000 people, we might end up with an average of 5 foot 11. Now, each of these samples is producing a slightly different estimate of the population mean. And if you were to keep on taking samples and plotting the means in a frequency distribution, what you would find is that they tend to cluster around a particular average. And so when we think of the sampling distribution of the mean, we need to also imagine that it too has its own standard error. So if we were to take lots of different samples and measure the heights of people, we would end up with an error measurement associated with the deviation and spread of those scores. And there's a special formula that we use for calculating the spread of the sampling distribution of the mean. And that's what we refer to as the standard error. And you can see here that the standard error is equal to the standard deviation divided by the square root of n. If that sampling distribution, the standard error, has a lot of variability, then we will have scores that look quite different from each other. We would have large amounts of variability. So if we were to take a sample of 1,000 people, measure their heights, and we had a score of 5 foot 5 inches, and then we took another sample of 1,000 people and we got a height of 6 foot 5 inches, there would be quite a lot of variability. We would be expecting to have quite a high standard error, and it would tell us that there may be a problem with our sampling. But what you would hope for if you have all things being equal is a relatively small standard error for the sampling distribution of the mean. So it's never going to exactly estimate the population mean, but every time you go and take a sample, you're going to get something that's kind of close to it. And all of those samples that you take and you calculate the average, you're going to get a roughly normally distributed set of averages or means around those samples. So the bigger the n, the smaller the standard error. So in this equation, the n that is going to be used underneath the standard deviation is square rooted first. And there's a particular quirk to be aware of there. What that's going to do is make the numbers smaller. And there is an aspect of diminishing return to that. So if you had a very small sample and you took the square root, for example, if you had an n of 4, then the square root's going to be 2. So with small samples, it's reducing the number quite dramatically. It's reducing it by 50%. And we know that when we reduce numbers and we divide by less, we end up with a bigger product at the end. But as samples get larger and larger, the amount that n is going to decrease gets considerably larger too. So if you had an n of 100 and took the square root, that would go down to 10. And if you had an n of 200, that would reduce to 14. So in some ways, this gives you some sort of insight and control over how large samples you may need to be trying to collect based on the effect you want the size of the sample to have ultimately on the standard error. So increasing a sample size from 100 to 200 isn't going to do much in reducing your value of standard error, but increasing smaller samples by a little bit more will start to have quite a big effect. And the effect there is that increasing your sample size and getting the sample size just right improves the measurements that you're making and the standard error associated with those. But let's try and put this in the context of an example. So imagine out there in the real world, on a particular memory task, for instance, people will score 125, and they will have a standard deviation of 10.5 associated with that. So those are the population mean and standard deviation, right? And theoretical estimates for this example. So we want to test whether ginkgo biloba can improve memory. So we take a sample of 20 people. We give them ginkgo biloba. We give them a memory test to complete, and then we're interested to look at their score. And in this example, that group of 20 people produces an average score of 130. So our question is, do the 20 people who are scoring 130, could they have come from the same population? Are they any different from the larger population's mean and standard deviation? So we want to decide whether the sample is from the same population. So should a score of 130 be considered similar enough to the population mean for us to conclude that ginkgo biloba doesn't really have an effect? And this is the inferential part. This is where we are engaging with the general linear model to help us make consistent decisions about reality. So we could look at the difference between these scores, 125, we've given people ginkgo biloba, now they're scoring 130. We might look at those and think, well, yeah, there's an improvement, so ginkgo biloba must improve memory. But does it? And that's where we need to use inferential statistics to help us as researchers make an unbiased decision or come to an unbiased answer to that question. So if you have a look at the calculations we went through regarding the Z-score, to calculate the Z-score, you're really interested in an individual score and how different that is from the average, and we would divide that by the standard deviation, because the standard deviation is the distribution that is related to the individual scores contributing to the mean. But what we're going to do now is use that same logic, but instead of testing an individual score, we're going to test the average that we've collected in our sample, and we're going to compare that with the population mean. And we're going to use the standard error in this equation because it's the standard error that is the deviation score associated with the standard deviations around the mean. So here are some of the numbers. If you look at this equation over here, first thing we're going to need to be able to do is to solve the standard error. And so we can know that the standard error is going to equal the standard deviation divided by the square root of n. And we've been given that piece of information from the population. So we know that the standard deviation of the population is 10.5. And we're going to divide that by the square root of 20 because there was 20 participants that we gave the ginkgo biloba to. And this gives us a number of 2.34. Now, over here in the equation again, we want to take the mean from our sample, 130, subtract the population mean, and then divide it by the standard error, which is 2.34, and this will give us a value of 2.13. So that's our Z-score in relation to the sampling mean. So some cool things about this are the proportion of area under a normal curve is equal to the probability of the scores. And so what we need to be able to do is to go to a Z table and look up the new type of Z score that we've calculated, which is 2.13. And when we do that, it will give us a value of 0.9834. And I'm just going to show you the Z table here. I know that's quite small, but there is a URL at the bottom if you wanted to go and find these, but they are easy to find on the internet with Google. What we want to do is we want to go and look up 2.13, and here on our Z table we've got 2.10123, and this gives us a value of 0.9834. 0.9834. Now you'll notice that it's giving us the probability of this region here that's in grey. So if you look at that diagram at the top, you'll see a diagram of a normal distribution with the shaded area. But we want to know if our value of 130 goes beyond that. Is it unusual? So, the probability that the sample with the mean of 130 was drawn from a population with a mean of 125 is 0.0166. That's because we've subtracted 1 minus 0.9834, and that gives us our 0.166. And here in the diagram you can see the region that's estimated. And it's just this little bit here in the tail. And our value of 130 would come in about here. This is our Z-score. We look up on the Z tables what portion of scores would be below 130. Well, it was 0.98, and here over 0.0166. So by convention we would say that anything with a P of less than 0.05 is quite rare, and here we've got a probability score of 0.0166, and so we would say that getting a sample with a score of 130 would be quite unusual if we would be drawing that from the true normal population. And because we're given ginkgo biloba to the participants in the study, we're going to make the logical leap to say that, well, it was the ginkgo biloba that has increased this score to make it an unusually high score that you would find in that population. So since 0.0166 is less than 0.05, we can say that the sample did not come from our population. We might conclude that ginkgo biloba actually improves your memory. Now, it's probably important for you to make sure that you have a very good and complete understanding of p-value and those points I was just going over. So please review them again and look for other pieces of information you can find on the internet to help you understand it more deeply. Non-psychologists find p-values quite arbitrary, and when they ask psychologists to explain what p-values mean and we don't have good explanations, it actually makes people a little bit sort of suspicious of the science that you're trying to communicate. So make sure you understand all of the concepts that you're going to rely on in quite good detail so that you can explain to people exactly the logic that you're using behind your own analyses. So back to hypothesis testing. Testing our best guesses about population distribution a priori. So think about what a hypothesis is. So we're just going to go back through that example and now introduce our scientific hypotheses and put the example in that context. Now, there are two types of hypotheses that researchers rely on. One we refer to as a null hypothesis, and this is simply the default position that there is no difference between the sample that we're drawing from the population and the true average of that population. So the null hypothesis would be that ginkgo biloba does not have an effect on memory, and that your sample mean, whatever you get, isn't going to be different enough from the true population mean for us to conclude that ginkgo biloba is memory enhancing. Alongside the null hypothesis, you will often find the alternative hypothesis stated clearly too. And this starts to tell us a little bit about what we think might happen. So if you wanted to have an alternative hypothesis, it might be that you've read some things about ginkgo biloba, and it might be that people think, yeah, there might be some way that it can have an effect on memory. And if it does, our hunch would be that it's going to improve it. So our alternative hypothesis, right, as opposed to the null hypothesis that there's no difference, our alternative hypothesis would be that our sample that we draw is going to be significantly higher when people have been taking ginkgo biloba. So the alternative's not always, proven. It's often just a best guess explanation, and there's often times where, you might want to have more than one alternative hypothesis as well. So tentatively, researchers choose an unbiased position and assume that the null hypothesis is going to be true unless otherwise proven. So, if the mean of our ginkgo biloba sample could have been reasonably obtained from the population distribution of an average of 125, then we would retain the null hypothesis. If the likelihood is very small that the result could have come from a population obtained with a distribution of 125, then we reject the null hypothesis in favor of accepting the alternative hypothesis. And in this case, we would be rejecting the null hypothesis and accepting the alternative hypothesis that ginkgo biloba does improve memory. So how much different does a sample mean need to be from the population mean? Well, yeah, there needs to be a difference, and we need to know whether that difference is significant or not, and that means that we need to know in advance what our rejection region criteria are going to be, and what our critical probability values are going to be before we make this decision about accepting or rejecting a hypothesis. Now, the probability that defines a boundary between rejecting or accepting the alternative hypothesis is called alpha, right? And alpha is generally a p-value of 0.05. And so if the probability we're able to see in our sample distribution in relation to the true population mean is less than 0.05 or alpha, then we would reject the null hypothesis and accept the alternative hypothesis. Now, some people see the p less than 0.05 as some sort of mythical or magical number. It's not. Psychologists simply use that by convention, right? And so we want to make sure that there's a less than 5% chance, right, of obtaining that value before we're going to conclude that manipulation, in this case the administration of ginkgo biloba, is going to make a difference. Some scientists will use a slightly more conservative p-value of 0.01, but generally speaking, what you're going to see in most psychology articles is an alpha level that is set at 0.05, with researchers really only bothering to talk about differences that are significant, right? Ones with probabilities less than 0.05. So, rejection regions. So what we want to be able to do here is go to the Z table and find a Z score that is quite close to 0.05, right? And if we were to do that, and we were to come down here to 1.96, this is accounting for a probability of 0.975, which is about the closest we can get. Here's one closer, 9495. 1.64. 1.64. So we know that a z-score of about 1.64 is going to be the z-score that is going to be a boundary between whether we're going to decide whether we want to consider something to be significantly different or not. So here's the table again, and you can go through there and find the probability of 0.05 and what z-score that is associated with that. So the rejection region. Now I want to introduce a term here around the one-tailed test. And so if you think of these portions here of the distribution curve at the ends as the tails of those distribution. In our ginkgo biloba example, where we have a population mean of 125, we're predicting that ginkgo biloba is going to improve memory. So our prediction is one directional. And when we look at our 0.164 value here, if we were to go through and calculate our z-score using the data that we collected in our sample, would be interested in knowing whether that z-score is bigger or smaller than 1.64. If it's smaller than 1.64, we're going to say that our sample is basically the same as the population sample. If it's bigger, we're going to say that it's a different sample, and then we're going to make a case to support the alternative hypotheses. So one-tailed test is used when we have a specification of the direction of the effect, and we're able to specify that direction a priori in advance of us collecting any data. So the direction that you're going to make your hypothesis in is just based on common sense, previous research, and theory that you've read about, right? So what do we know about ginkgo biloba, and then what would that lead us to predict? And that's the sort of thing that you need to be able to do as a researcher, is not just propose randomly different hypotheses, but propose hypotheses that are based on, as much as possible, what we already know. There's another type of test, the two-tailed test. And this is a test when we're not sure about the direction of the effect or treatment that we're interested in. So it might be that you're reading research on ginkgo biloba, and some of the research shows that it doesn't improve memory. In fact, it kind of makes it worse. And other research shows that it might have a memory-enhancing effect. Well, then we're in a little bit more of a difficult situation. The direction of our effect is not quite so obvious. So we would choose a two-tailed test because we're not able to specify a direction. So our alternative hypotheses might be that it could improve memory, but we might need to include another hypothesis as an alternative that it decreases memory performance as well. So what's the rejection region when we have a two-tailed prediction? Well, in the Z table, when we're looking for the 0.05 here, we've got to be able to account for the possibility that the score might also be in the other end of the tail. We want to deal with the probabilities of less than 0.05, and that means that we need to divide that to 0.025 at this end and 0.025 at that end. So if we go into the Z table, now we're trying to find what the Z score is that's closest to the probability of 0.025. And we look in the table, and that is 196.9744. So our critical value for Z, if we're doing a two-tailed test, would be 1.96. So the alpha is still 0.05. We're still interested in occurrences that have got less than a 5% probability, but we've divided it by 2, and here you can see at the ends of each of those distributions and in the tail we have calculated a new rejection region, which is now 1.96. So we're looking for z-scores that we calculate from our sample with either values that are going to exceed 1.96 or be below 1.96 over here. So it's harder to get a significant result if you've got a two-tailed test because they're less powerful and more conservative. But you want to use a two-tailed test unless you have very good theoretical reasons for making a stronger one-tailed prediction. And I would say it's fair to say that lots of psychologists would opt for a two-tailed test because, first of all, it's more conservative and it does cover you for the eventuality that your experimental research pops up some unexpected findings that you might not have been able to account for in advance. So let's look at these equations. It's not hard to imagine this logic can be applied to testing for experimental differences. So if you look at this z-score equation here, z equals the mean minus the population mean divided by the standard error. It might be that if you were to do a piece of research and you had two groups of people, one group of 20 people who don't take ginkgo biloba and another group of 20 people that do take ginkgo biloba, it might be that you could take the averages of those two groups, subtract them from each other, and then divide by some error measurement, and then that would start allowing us to be able to apply some of the logic around normal distributions and z-scores to experimental design and research.